Current state-of-the-art 4D reconstruction methods enable the reconstruction of captured motions using coherent 3D geometry and texture that deform over time. In this example, a walking and a jogging pose are captured and reconstructed. Although the underlying geometry is coherent across poses, the texture is not, because of inherent appearance changes in the captured imagery. This causes severe blurring and ghosting artifacts when interpolating across captured poses, which is most visible on the face of the character. We seek to capture these dynamic appearance changes using a space-time parametric appearance model. We introduce 4D model flow, a novel representation to compute and store dense appearance correspondences across 4D models. Here is an overview of our approach. We first project the captured appearance onto a common geometry proxy and render it from a set of canonical camera viewpoints. In this example, both the walking and jogging appearances are projected onto the walking geometry. We evaluate the visual discrepancies between each pair of corresponding cameras using dense optical flow. The computed flow fields are projected from the camera screen space to 3D space and then converted to a 2D local representation on the surface of the geometry, independent of camera viewpoint. The generated 4D model flow encodes a parametric appearance model of the input pair of 4D models. Here we show the texture maps from two computed poses and the computed 4D model flow. The base UV map encodes correspondences of each pixel of the walking appearance to itself, and the flow UV map encodes the correspondences between the walking and the jogging appearances. For illustration purposes, we show the difference between these UV maps to visualize the detailed local correspondences between the two surface appearances. Our 4D model flow enables view-independent, video-realistic interpolation across 4D models without the need for appearance alignment computation at runtime. Here we present two captured 4D models corresponding to a walking and a jogging pose. When interpolating between these two poses, the linear interpolation of the appearance results in ghosting and blurring artifacts. These are particularly visible on the face, both in 3D and in the texture map. Our approach mitigates such artifacts using the precomputed 4D model flow to warp appearances before blending them. This results in free viewpoint parametric appearances that maintain the input video quality. Here we can see a comparison between our proposed method and linear interpolation next to the input poses. We now show how our approach successfully interpolates between 4D videos. In this example, we interpolate between a walking motion on the left and a jogging motion on the right. Notice the significant difference in visual appearance dynamics between these sequences. We now interpolate the halfway motion between the two input motions. Also, interpolating the appearance linearly fails to reproduce the expected appearance dynamics and leads to ghosting artifacts. This is also shown in the heat map that visualizes the magnitude of flow vectors between the aligned input appearances. 4D video textures mitigate ghosting artifacts by performing appearance alignment at runtime. This heavily affects the overall performance and limits the practical uses of 4D video. Our 4D model flow achieves similar visual quality as previous appearance alignment approaches with an order of magnitude speedup. This enables 4D video interpolation at frame rates of over 100 frames per second. Notice in this side-by-side comparison how our proposed approach successfully aligns non-rigid appearances, such as the hair motion, to synthesize plausible interpolated surface dynamics. Our approach can also be used to synthesize parametric facial expressions by interpolation. This dataset has been geometrically aligned with sub-millimeter accuracy across the expressions using a state-of-the-art facial surface tracking method. Even in such a geometrically accurate dataset, our 4D model flow improves on the existing alignment with the linear blending of the appearances. These differences are better appreciated in this comparison at the halfway position. Here is another example in which a neutral and a puff expression are interpolated. Notice the large error in alignment around the eyes when using the linear approach. Our 4D model flow minimizes such artifacts while performing at real-time frame rates. Finally, we show a full body pose interpolation of a female character. Notice how non-rigid surfaces like the t-shirt and the long hair make appearance alignment very challenging. Thank you for your attention.